Here we have been provided a problem statement. It is, suppose that the input to an FIR LMS adaptive filter is a first order autoregressive process with an autocorrelation provided as small r suffix x as a function of k, that is equal to c multiplied to the alpha having the power denoted by mod k, where c is greater than 0 and alpha is greater than 0 but less than 1. Suppose that the step size denoted by mu is given as mu is equal to 1 upon 5 times lambda max. Now the question or the problem statement is having 3 tasks to be accomplished here in the parts A, B and C. In the part A, we have the question, how does the rate of convergence of the LMS algorithm depend upon the value of alpha? Whereas the part B question is, what effect does the value of C have on the rate of convergence? Whereas the part C is, how does the rate of convergence of the LMS algorithm depend upon the desired signal D of n? See, for the given problem statement, we have to have a consideration of the design of finite impulse response adaptive filter utilizing the least mean square, that is LMS algorithm here. And to this adaptive filter, there is a consideration that the input is a first order autoregressive process. See, in the chapter number 3, that it was discrete time random processes, we have seen the fundamental details of what exactly the random process mean, what are the various types of the random processes and the corresponding characteristic features. Thereupon we have learned few of the special types of the discrete time random processes. So there it was AR process, MA process, AR-MA process. So AR process standing for the autoregressive process. So here it is the case as input signal, that is first order autoregressive or the AR process. For this input signal, we have been provided the information regarding the autocorrelation sequence here, that is denoted as Rx of k, that is equal to c into alpha to the power mod k. C is positive greater than 0, alpha ranges greater than 0 but less than 1, and we have been provided the step size. So as we see part A question, how does the rate of convergence of the LMS algorithm depend upon the value of alpha? So let us answer this particular part A question here. So for that purpose, let us recall the concepts of maximum lambda and minimum lambda. See, the lambda max and lambda min are bounded by the power spectrum or the power spectral density that we usually denote by capital P suffix x as a function of e to the power j omega. So we have lambda max less than or equal to the maximum power spectral density capital P suffix x as a function of e to the power j omega. So here with the given details we can express it to the form c multiplied to the ratio 1 plus alpha divided by 1 minus alpha. Whereas we have minimum lambda minimum greater than or equal to the minimum as a function of frequency, the power spectral density denoted by capital P suffix x as a function of e to the power j omega. This is equal to c multiplied by 1 minus alpha divided by 1 plus alpha. So the limits of the maximum lambda and minimum lambda associated to the power spectrum we have here, and since the time constant for the convergence here it is proportional to the condition number, and for the large value of the size denoted by p here, we have the number denoted here with the Greek letter as a ratio of lambda maximum to the lambda minimum. This is approximated to the square of the ratio where numerator is 1 plus alpha and the denominator is 1 minus alpha. So to look at this particular relation as the value of alpha increases, the tau also increases and the convergence is slower. So the question it was, how does the rate of convergence of the LMS algorithm depend on the value of alpha? So this is what the answer. With the increase in alpha, the tau will increase and the convergence will be a slower one here. Now the part B question is, what effect does the value of C have on the rate of convergence? See, the solution to this part B, as the constant C will change, the eigenvalues are scaled by C here. However, the condition number that we have the formulation with the Greek letter as a ratio of lambda max to lambda min approximated to the square of 1 plus alpha divided by 1 minus alpha. This will be totally unaffected here. There is no role of C here. So therefore C does not affect the time constant for the convergence here. The question was, what effect does the value of C will have on the rate of convergence? The rate of convergence we have shown that is not at all depending on the C, so it is not at all being affected here. So this is the answer to part B here. Now the part C question is, how does the rate of convergence of the LMS algorithm depend upon the desired signal denoted by D of n? See, the desired signal D of n will have no effect on the rate of convergence. There is no role you see in the formulation of that convergence rate here. That is why the answer for part C will also be same, that there is no alteration, no effect of the desired signal on the rate of convergence here. So this completes our problem number 4 based on to the understanding of the convergence of the LMS algorithm when a special type of the discrete time random process is fed as input to it with the given characteristics of the autocorrelation and the step size along with the parameter ranges here.